Today's video is going to include more audio than writing necessarily, so there's a lot of text and visuals as well to help you follow along. The essential question here is, in this section we use tables of values and graphs of functions to answer the question, what happens to the values of f of x of a function f as the variable x approaches the number a? Today we're starting limits. This is the beginning of calculus, and it is in chapter 12 of your pre-calculus book. The definition of a limit. So we begin by investigating the behavior of this particular function, a parabola, for values of x near 2. So we're going to plug in values near 2, but not equal to 2. Okay, so they started off with plugging in 1. If they plugged in 1, they got 2. When they plugged in 1.5, they got 2.75. This could take a while. So continuing on, as you see, 2 will lie directly between 1.999 and 2.001. So as x is getting closer and closer to the value of 2, what does f of x appear to be getting closer and closer to? 3.997? 4.003? Yeah, it looks like it's approaching 4. Graphically, you can see as x approaches 2, it is approaching 4. The notation for this is the limit. As x approaches 2 of this function, x squared minus x plus 2 is equal to 4. Now, couldn't we just have plugged in 2 and gotten 4 and called it a day? Well, sometimes that works, but that's not what a limit is. The limit is not necessarily the f of x value, because even if there's not an f of x value at a, there can still be a limit. Definition of a limit. We write this, we say this: the limit of f of x as x approaches a equals L. And we can make the values of f of x arbitrarily close to the limit L, as close to L as we want, by taking x to be sufficiently close to a but not equal to a. So in order to see what was the y value, or the f of x value, approaching when x was approaching 2, we actually plugged in a bunch of numbers, or the book did, of x values that approach 2. And so by seeing the pattern of the y values, we could deduce that f of x was approaching 4 as x was approaching 2. Notice the phrase, but x is not equal to a in the definition of limit. This means that in finding the limit of f of x as x approaches a, we never consider x equal to a. Okay? In fact, f of x need not even be defined, like I said. Okay? Here's an example. As you're getting closer and closer to a, what is f of x approaching? It's approaching L. So as x gets closer to a, so as x approaches a, f of x approaches the limit L. But if x is equal to a, f of a, that's undefined. See, you've got a hole here. Undefined. So even if the value is undefined, there can still be a limit. Guess the value of the limit of x minus 1 over x squared minus 1 as x approaches 1. Check your work with a graph. So now we're going to create the table. And what values do we choose for our table? I like to put the value that x is approaching in the middle. And then I am going to require that you include 3 values to the left of that number and 3 values to the right of that number. So the values I'm going to choose for my table include values that are very close to 1. So 0.999, and this would be 1.001. And then I'm going to take away a 9, take away a 0, just so I can get a clear picture. These are the values I'm going to plug in. I'm going to fill out the table now. Here is the table. So as you can see, as x approaches 1, f of x seems to be approaching, we have 0.500, 250, and then 0.499. It seems to be approaching 0.5. Let's check our work with a graph. Here I graphed it on Desmos, and yeah, you can see as x is approaching 1, the f of x value is approaching 0.5. But if you zoom in closer, you actually have to click on the point for it to show up on Desmos. At 1, there's no value. F of x is undefined. There's literally a hole there. F of x can be undefined, and you can still have a limit because it's not what exactly is the value of f of a necessarily. It's what is f of x approaching as x approaches a. Continuing on, use the table below to find the following. Find the limit of square root t squared plus 9 minus 3 all over t squared as t approaches 0. So they already gave us a table. Awesome. What does it appear to be approaching? They put plus or minus because whether you put it in a positive or a negative, both times it's being squared. So this is giving you a picture from both sides already. And it looks like it's approaching this number, 0.166666666. Okay, repeating, that number as a fraction is 1/6. Great. So the limit of this function is 1/6. But what would have happened if we had taken even smaller values of t? Smaller and smaller and smaller values should give you a more accurate answer of what f of x is approaching. Ooh. It appears that f of x is actually approaching 0. So what is it? Is the limit 1/6 or is it 0? Here's the thing. If you try these calculations on your own calculator, you might get different values, but eventually you'll get 0 if you make t sufficiently small. Does this mean that the answer is really 0 instead of 1/6? No, it does not. The limit is 1/6. In fact, when t is sufficiently small, a calculator's value for t squared plus 9 is 3. Okay, it's as many digits as the calculator is capable of carrying out. When you graph it, this is what it looks like. Now you zoom in to graph B. This is another clear picture of what it looks like. Zoom in further. Zoom in further. Graphs C and D give you an inaccurate look because as you plug in values for t sufficiently small, closer and closer and closer and closer to 0, your calculator has a difficulty accurately depicting what's happening with the graph because there are so many decimal places, okay? It's too much to keep track of. I am guessing Desmos would give you a clearer graph than maybe what they used here. But we'll come back to this example at the beginning of tomorrow's lesson. Limits that fail to exist. Guess what? Not everything has a limit. The Heaviside function h is defined by, this right here is called a piecewise function because the function is defined by two pieces, right? H of t is 0 if t is less than 0, but h of t is 1 if t is greater than or equal to 0. So you have these sort of restrictions because they're piecing together parts of other functions to create a new function. Okay, Oliver Heaviside, an electrical engineer, created the Heaviside function in order to represent an electric current that is switched on at t equals 0. Okay, so here there's no electric current, turn on the light, bam, electric current. Okay, there's a huge jump. It's either off or it's on. It's 0 or it's 1. A limit that fails to exist, a function that oscillates. Okay, so I decided to plug in some values into the table so we could see what is going on as x approaches 0. Okay, so, this seems pretty clear that the limit is approaching 0. Now, before we look at a graph, I decided to plug in maybe a less convenient fraction, such as 2 over 25. Okay, what happens when we plug in 2 over 25? So when we plug in 2 over 25, we actually get sine of pi halves, because that's coterminal to 25 pi over 2, which is 1. So literally right next to where we were going. As we got smaller, we went to 1? So then, did we just choose bad fractions? What is happening here? Let's take a look at the graph. This is an oscillating function. It is bouncing between 0 and 1 so fast, okay, that the limit does not exist. It is just jumping up and down between these values. I decided to graph this on Desmos. As we continue to zoom in, it's really hard to zoom in because there are so many lines, and you can only zoom in by touching the white spaces. Okay, yeah, this is crazy. This is an oscillating function, really zoomed in. That's why the limit doesn't exist. Find the limit of 1 over x squared as x approaches 0 if it exists. Okay, so as you choose values that are closer and closer to 0, what's going to happen? I chose fractions because I wanted to do the problem in my head. You can write it as decimals if you're doing it in a calculator. And as you can see, as you get closer and closer to 0, it appears as though your numbers are just getting bigger and bigger and bigger. So then one may pose the question, why can't the limit be infinity? The limit does not exist.